In the H2 math syllabus, vectors is one of the biggest single topics, and there are many new operations, formulas, and cases to remember. In this first part of the vectors lessons, we will cover the basic operations required. A vector is a quantity which brings us from one point to another. For example, if we have 2 points, A and B, what a vector does is, if we have a vector AB, it brings us from vector A to vector B, and we write it like this. Okay, from point A to point B, and an arrowhead above AB. Likewise, if I have points D and E, the vector DE will bring me from point D to point E, and this is represented by the vector DE with an arrow on top. If a vector starts from the origin, then the vector is called the position vector of a point, since it brings us from the origin to the position of the point of interest. For example, if we look at point P over here, which has coordinates of 2, 4, 3, we say that the position vector of point P, which is the vector OP, is written as 2, 4, 3. Okay, this is called a column vector form, and the three components over here refer to the X component, the Y component, and the Z component. How it works is, if we start from the origin, we are first going to move in the X direction by 2 units, hence the 2, followed by 4 units in the Y direction, hence the 4, and finally we are going to move vertically up in the Z direction by 3 units to get 3. So the column vector 2, 4, 3 simply refers to the number of units we move in each direction before we arrive at the final destination. Another form that we can represent a vector is the ijk format over here, where I, j, and k, they refer to vectors which have a length of 1 unit, and they are parallel to the x, y, and z axis respectively. Therefore, the column vector 2, 4, 3 can be written as 2i plus 4j plus 3k. So this is the ijk format. So other than naming the vector OP, we can also give it a name, like for example vector A. So for these ABCs over here, if we are using it to name any vectors, since they are not scalars, we will have to identify and distinguish them from normal scalars. And how we can do so is, if the names are being typed out, they are usually bolded. But if we are doing a handwriting, we will not be able to bold all these alphabets, and therefore what we can do is simply write it as normal, but we will put a squiggly at the bottom to represent that it is a vector. Similarly, point Q, it has a coordinate of 0, 4, 0, and therefore we can write its position vector as B equals to OQ equals to 0, 4, 0, or simply just 4j. Let's see how we can define position vectors using example 1. For OA, we start from the point O, and we want to arrive at the point A. So let's move in the X direction first, which we will move by 5 units since it is half of 10, but it is in the negative X direction since I is defined to be the right hand side direction and we are moving to the left. So for OA, the first component will be a negative 5, followed by, now if we are moving in the Y direction, we will be moving downwards by 2 units, which is negative 2 since it is in the opposite direction as the J vector. And finally, we are moving upwards by 3 units, and therefore the third component will be 3. Similarly, we can find OD to be equals to minus 5, 2, and 6. And OG will be equals to 5, 2, 0. Like scalars, vectors can also be operated on. The two simplest operations are the addition and subtraction. Geometrically, these are how vectors look like. when we add or subtract them. If we start from a certain point and we subject this point to a vector of a plus b, what happens is we can simply decompose this vector a plus b into two consecutive movements. First, we move this point, the starting point, by a vector a. Then once it reaches its first destination, we will move it by vector b. And therefore, we see that they will both end up at the same destination. For subtraction, there is a slight change that we need to do because for the vector b, we can rewrite it as negative b, where we have the same vector but it is now pointed in the opposite direction, and we can therefore add these two vectors up, a and negative b. So we have a certain starting point, we will move it by a first, followed by negative b to end up with this third point over here, which is the same final point as the vector a minus b. Numerically, how we can perform this addition and subtraction is very easy. We simply just have to add or subtract the individual components up, and we will end up with the third vector, which is the result of addition or subtraction. If you are given 2 points P and Q and we want to find out the vector that brings us from point P to point Q, i.e. vector PQ, we can make use of this formula over here. PQ equals to OQ minus OP. And how it is derived is very simply, if we look at the geometry over here, to bring us from point P to point Q, we can take a detour to move from point P to point O, and subsequently from point O to point Q. Therefore, we can write PQ as PO plus OQ. And PO, we can rewrite it as negative OP. Since PO and OP, they are the same vectors, just that they are pointed in opposite directions. Plus OQ. And if we are going to rearrange these two terms, I can therefore write it as OQ minus OP, which is the same as the formula given above. All vectors consist of two components, a direction and a magnitude. The magnitude tells us how long or how short the vector is. It is the length of the vector. Now, if we have a vector A, which is defined as a column vector of x, y, z, then the magnitude can be written as mod A, where mod over here refers to the magnitude of vector A, equals to the square root of the three components squared and sum, so x squared plus y squared plus z squared. This formula over here is derived simply using the Pythagoras theorem. In example 2, we have the same diagram as example 1. Now, we are asked to find the vectors AG and DG and their respective magnitudes. So from example 1, we know that OA equals to minus 5, minus 2, and 3. OD equals to minus 5, 2, and 6. And OG equals to 5, 2, 0. And therefore, vector AG can be found using vector OG subtracting vector OA, which becomes 5, 2, 0 minus negative 5, negative 2, and 3. And this gives us 10, 4, minus 3. Likewise, DG can be found using OG minus OD, which is the same as 5, 2, 0 minus away minus 5, 2, and 6, which gives us 10, 0, minus 6. And with these two vectors found, we can find out their magnitudes very easily. Mod AG will be equals to square root of 10 square plus 4 square plus 3 square, which becomes square root 125, and mod of DG will be equal to square root of 10 square plus 0 square plus 6 square, which gives us square root 136. The unit vector is a vector which has a magnitude of 1 unit, hence the name unit vector. For any vector, its unit vector can be represented simply by adding a cap above it, like this. Or if we are writing in this form over here, we can also put a cap above the arrow. To find out the unit vector of any vector, we can simply use this formula over here, where a cap equals to a, which is the actual vector, divided by its length. So this gives us the unit vector. Conversely, if I'm going to cross multiply this mod a across to the other side, I will end up with this formula over here. And this is a very useful formula because it decomposes any vector into two components. Number one, its length, and number two, its direction. And finally, in example 3, we are asked to find out what are the unit vectors of vector AG and DG, which we have found earlier in example 2. Therefore, for vector AG, if we apply the formula, it will be vector AG divided by mod of vector AG, which gives us 1 over square root 125 multiplied by the vector 10, 4, negative 3. And for vector dg, its unit vector can be written as vector dg divided by its length, which gives us 1 over square root 136 multiplied by 10, 0, negative 6.